Question number 8. The question number 8 is that an inclined plane ends into a loop of radius r. Find the minimum height from where a particle shall slip so as to loop the loop. So first option here 5r by 2, second option 5r by 3, third option 5r by 4, and the fourth option 10 by 3r. Now see how to do this problem. So question is this: first of all, understanding of a question. This is your inclined plane, and this inclined plane convert in the form of a loop of radius r. Now they are asking what could be the height. What could be the height from where the particle should be released? Let particle should release from height h so that it can follow the at least your complete cycle. See, to follow the complete cycle, what is the minimum velocity at the highest point? When the particle will be here, so let velocity of particle your UH. So forces on the particle, one is your N, another your mg. So these two forces N and mg provide required centripetal force. N plus mg or m UH square by r for minimum UH. For minimum value of UH, N should be 0. So UH minimum. Now N is 0, UH minimum is equal to your root over G into R. The minimum value of velocity at the highest point should be root gr. Now we can apply conservation of energy from here to here, considering this as a reference. So potential energy here your mgh, here potential energy mg into 2r plus kinetic here half m UH square, which is your gr. So this will be your 5 mgr by 2. So h should be your 5r by 2. So this is the our correct answer. So option number 1 is the correct option. So option 1. Now see the question number 9. Question is this: a particle slips from a height 4r from an inclined plane which ends into a loop of radius r. Find the normal reaction at the highest point and at the lowest point. The first option your 3 mg and 9 mg. Second option 3 mg and 6 mg. Third option 0 and 6 mg. And the fourth option your 4 mg and 8 mg. See, it's a very similar problem as we did in the last problem. This is the inclined plane, and now a particle has been released from a height 4r. So they are asking what is the reaction, normal reaction at the lowest point and at the highest point, at these 2 points. See, let velocity at lowest point your UL, velocity of this here at highest point your UH. Here normal reaction NH highest point here, and another force here mg. Here mg your downward and normal reaction NL your upward. First, we can write equation at the lowest point. Equation at the lowest point is your NL minus mg is your m UL square by r. This have radius your r. The reaction at the lowest point written as mg plus m UL square by r. This is your first equation. Similarly, for second equation, NH plus mg m UH square by R. So here NH will be your MUH square by R minus Mg. This is your second equation. Now we can apply conservation of energy equation. Here potential energy Mg into 4R. Here kinetic energy half M UL square, no potential, and here kinetic half M UH square plus potential 2 mgr. From third equation, see, from equation 3, check it, 1 mm cancel, 2 into 4 8, the UL is equal to your 8 gr, and see, from this is your 4 mgr, this is your 2 mgr, this 2 mgr into 2, the UH is equal to your 4 gr. Substitute the value of UL and UH in this equation. So NL is your Mg plus M by R UL square. UL square means 8 gr. This will be your 9 Mg, and highest point UH NH M UH square by M UH square your 4 gr minus Mg. So this is your 3 Mg. So reaction at the highest point your 3 Mg and normal reaction at the lowest point your 9 Mg. So our correct option your option number 1. Question number 10. A particle has velocity root over 2 rg at the highest point in a vertical circle of radius r. Find the ratio of normal reaction at the highest to the lowest point. First option 1 by 7, second option 1 by 3, third option 1 by 5, and fourth option your 2 by 9. See the method of solving the problem. See, this is your vertical circle of radius r. It is given here highest point particle have velocity or root over 2 rg. So they are asking ratio of normal reaction at the lowest and highest point. So let velocity at the lowest point your UL, reaction at the lowest point NL, and this NH. So they are asking the ratio of the normal reaction at the highest to the lowest, NH by NL. So see, first from the this diagram at highest point. For highest point, NH plus Mg is your M UH square by R. UH square is your 2 Rg. So this become your NH is your 2 Mg minus Mg, your Mg. This is your first result. Now at the lowest point. For lowest point, NL your upward minus Mg, M UL square by R. NL is your Mg plus M UL square by R. Now we will find velocity at the lowest point from conservation of energy. From energy conservation. Half m UH square plus mg into 2r is equal to half m UL square. UH square is your 2rg, 2 and 2 cancel, so mgr plus 2mgr MUL square by 2. So, UL square is equal to your 6 GR. So, check it. Now, from equation 2 and 3, check the equation 2 and 3. Equation 2 is this, 3 is this. So, N at lowest point, mg MUL square by r. MUL square by r is your 6 mg, 7 mg. So, NH by NL is your mg by 7 mg, which is your 1 by 7. So, our correct option is your option number 1. Option number 1 is the correct option. Question number 11. A uniform rod AB of mass m and length 2a is falling freely without rotation under gravity with AB horizontal. Suddenly the end A is fixed when the speed of the rod is v. The angular speed with which the rod begins to rotate is, the first option your v by 4a, the second option your 3v by a, third option your 3v by 4a, and the fourth option your 4v by 3a. See 4a. As per the question here, this rod is given AB. Rod AB of mass m and length 2a. Now it start falling and the center of mass have let velocity v. Suddenly when the end A is your fix, now this is your fix. So, it should be like horizontal, but it is your let like this. So, this is the angular velocity of the rod. So, we can apply conservation of angular momentum about point A. On applying conservation of angular momentum about point A, initial angular momentum m into v a, final half I into omega. The moment of inertia about one of the end, that your ml square by 3. So, m L length here 2a by 3 into omega. So, omega is equal to your 3 mva by 4 m into a. So, this is nothing, m and a one cancel. So, it will be your 3v by 4a. This is the angular velocity. So, our option number 3 is the correct option. So, hence answer here, answer number 3. Now, see question number 12. The question is this: a rigid body rotates about a fixed axis with variable angular velocity equal to alpha minus beta t at time t, where alpha and beta are constant. The angle through which it rotates before it stops is, the first option you are given alpha by 2 beta, second option alpha square by 2 beta, third option alpha square by beta, fourth option alpha by 2 beta square. See, as per the given information, angular velocity is given here alpha minus beta t, and they are asking after how much time, after how much angle it rotate before coming to rest. So see here, before coming to rest means omega will be 0. So when it comes to rest, omega will be 0. That gives us t is equal to your alpha by beta. Now, so in this time we have to find how much angle it rotates. See, as omega is your alpha minus beta t, omega can be written as d theta by dt, alpha minus beta t. So d theta is your alpha minus beta t into dt, and then integrate. Time is your from 0 to alpha by beta. So theta is equal to your alpha t minus beta t square by 2, 0 to alpha by beta. Now simplify alpha square by beta, and this is your alpha square by 2 beta. 2 beta. So finally answer is your alpha square by 2 beta. So theta is equal to your, so our correct option is your option number 2nd. So answer 2 is the correct answer. Question number 13. It is given as a constant power is supplied to a rotating disc. Angular velocity omega of the disc varies with a number of rotation n made by the disc as, where first option is given omega is proportional to n cube, second omega is proportional to n square, third is omega is proportional to n to the power 1 by 2, and fourth is omega is proportional to n, where n is the number of rotation made by the disc. See, so power is constant, power P is constant. The power P is written as we know, torque into omega, and that is your constant here. So torque we can say I into alpha into omega, that is your power, and alpha is your, can be written like this, d omega by dt into omega. This further we can write I is your d omega by dt, number of rotation, d theta by d theta into d omega by dt into omega. So d theta by dt is again omega. So this power is equal to I omega square d omega by d theta. So theta is the, from here we can write power and I constant. So omega square d omega is equal to some constant into d theta, and d theta is the number of rotation. So see here, when we are integrating here, the omega cube by 3 k into theta. Theta is the angle rotated by this, and that theta can be said as 2 pi n. So then finally we can say omega is proportional to n to the power 1 by 3. So our correct option is your option number 3. Omega is proportional to n to the power 1 by 3. Question number 14. The question is given as velocity of center of a smaller cylinder is v. There is no slipping anywhere. Then find the velocity of center of mass of the largest cylinder. So first option your 2V, second option your V, third option 3V by 2, and fourth option your 5V. And now see the correct answer here. As per the question here, there are two cylinders. And these two are kept like this. One is like this and another is your kept over the other like this. So this have total your 2R, this your total have your 4R, and while this have your 2R as per the given question here. See, it is given velocity of the center of the smaller cylinder your V. So if there is no slipping anywhere, so this point also must have velocity your V and 2V. So this also must have velocity your 2V. So 2V velocity means here, let the velocity of this your V dash and angular velocity your omega dash, V dash plus 4R means 2R into omega dash, that is equal to your 2V. And as there is no rolling anywhere, the V dash must be equal to this, no slipping anywhere. So 2V dash is equal to 2V. The V dash must be equal to your V. So velocity of center of mass of the bigger cylinder will be also V. So correct option, your option number 2 is the correct option. Question number 15. It is given as a system of uniform cylinders and plates. It is shown all the cylinders are identical and there is no slipping at any contact. Velocity of the lower and upper plates are V and 2V respectively as shown. Then the ratio of the angular speeds of the upper cylinder to the lower cylinder. So our first option is your 1 by 2, second option your 2 by 3, third option your 1, and fourth option your none of these. So here the question is like this. See, there are two cylinders and these two are kept in contact with the plates, like this is your 1 and this is your another. So as per the question here given, this plate have velocity V and this plate have velocity 2V and there is no slipping anywhere. So we have to find the velocity of ratio of angular velocity of the upper cylinder to the lower cylinder. Let upper cylinder have angular velocity omega 1 and omega 1 and lower cylinder have velocity omega 2 and omega 2. See, first of all, this topmost point have velocity V. So the velocity of point of contact. See, if I am talking about the upper cylinder, this point must have velocity R, and this point, see, this point have velocity V and this point have velocity as per this your 2V. See the meaning of this. So if we are looking the, let velocity of the center of mass your V1. So see here, V1 plus R omega 1 is equal to your 2V, and here R omega 1 minus V1 is equal to your V. So we can have 2R omega 1 your 3V, omega 1 your 3V by 2R. Similarly, see for the lower block, this have velocity or V, and this have velocity or 0. See how to get then? Its angular velocity given here your omega 2. Let this have velocity of center of mass your V1. So what we can write? V1 plus R omega 2, this is equal to your V, and here V1 minus R omega 2, V1 minus R omega 2, that is your 0. Just subtract this, minus plus minus. So omega 2 we are getting V by 2R. So omega 1 by omega 2, check it, 3V by 2R by V by 2R. So this is your 3. So our correct option your option number 2, option number 2. So this is the question number 15. Question number 16. Question is that a spool shown in the figure is placed on a rough horizontal surface and has inner radius R and outer radius capital R. The angle between the applied force and the horizontal can be varied. Then find the critical angle for which the spool does not roll and remain stationary is given by. The first option your theta is equal to cos inverse small r by capital R. Second your theta is equal to cos inverse 2r by capital R. Third option theta is your cos inverse root r by capital R. And the fourth option your theta is equal to sin inverse root over r by capital R. Now see how to do this problem. As per the given question here, so here one spool is given, and this spool have inner radius R, outer radius capital R, and this is kept on a rough surface here. So this is your horizontal line. One force F is applied here, makes an angle theta with the horizontal. So we have to find what is the value of theta such that spool does not roll and remain stationary is given by. See, if we are talking about the torque here, that will apply torque in such a manner that this point of contact can have velocity in the horizontal direction. So this point will move in that side, so we can apply a friction force in this direction. Now see the equation here. If we are writing the equation for your horizontal, so our equation will be like this: F minus F is equal to your m into a. Another equation here, this will provide a torque F into R, or see, first equation we can say F cos theta minus F is here, and second equation this will provide a torque in your anti-clockwise direction, this is your clockwise direction. So F into R minus F into capital R is your I into alpha. I is the moment of inertia. Now from here we can write F small r by capital R minus small f I alpha by R. So from this we can write here for no slipping, for no slipping we can use A is equal to your R into alpha. So equation number 3 becomes FR by R minus F I alpha. I can write A by R square. Now see the equation from first and fifth. From first and fourth equation we can write F cos theta minus F R by R is equal to your MA minus I A by R square. I is the moment of inertia, that we can say MR square by 2. MA minus, or A we can take common, F minus M minus I by R square. Now for no motion A must be 0. If A is 0, so cos theta minus R by R will be 0. So cos theta is equal to your R by R. So theta value we can get a cos inverse R by R. So our answer is your answer number 1 is the correct option. Now question number 17. The solid sphere of mass capital M and radius capital R is initially at rest. The solid sphere is gradually toward onto a truck moving with constant velocity. So what is the final speed of the sphere's center of mass in ground frame when eventually pure rolling sets in, where V0 is the speed of the truck? First option given here 5 V0 by 7, second option 2 V0 by 7, third option 3 V0 by 7, and fourth option 7 V0 by 2. See the problem. It is given a truck, let this be your truck, which is moving with velocity V0 here like this. Now a sphere of mass M, radius R kept on that. So we have to find the velocity of the center of the sphere when pure rolling starts. See, for sphere, if we are looking for a sphere, so this truck is moving with velocity V0. The point of contact of truck is going in that side, the friction on the truck left side, the friction on the sphere is your right side. That friction provides the velocity to the truck, velocity to the sphere, as well as angular velocity also. So we will calculate the velocity v and angular velocity omega after time t. See, so v is equal to your u plus at A is nothing F by m into T, and omega your alpha T, alpha your torque F into R by I into T. Now, when rolling start, at the time of rolling, velocity of contact point C with respect to truck T must be 0. The velocity of contact with respect to ground plus or minus velocity of truck with respect to ground should be 0. See here, as omega in this direction, V also in the same direction. So, V plus R omega must be equal to V naught. So, V R omega we can get from here F R square by I into T V naught, and F into T we can put from here m into V. See, now from equation first, see, V plus F into T we can write m into V, F into T m into V, R square by I moment of inertia. This is a solid sphere. I will be a 2 by 5 mr square. 2 by 5 mr square, which is equal to V naught. So, mr square cancels. V plus 5V by 2 is your V naught. V is equal to 2V naught by 7. So, this is the correct option. So, option number or answer number 2 is the correct answer.